7b is also a common ion effect or Le Chatelier's principle with solubility, but in this one, we're looking at it in terms of an acid or base. So we have solid magnesium hydroxide, which dissociates like this. So it gives me the hydroxide ion. It gives me this KSP down here. The 2 becomes my exponent, but it tells me I have a pH of 11. So that means when my pH isn't 7, that I either have a higher or lower concentration of hydroxide or hydrogen ions. In this case, it's extra hydroxide. It is a basic solution. The pH of 11 means that I can do 10 to the negative pH to get my hydrogen ion concentration. We will practice all of these equations again in our acid-base unit. But they are things we're hopefully familiar with from previously in chemistry. Then we know this equation right here allows us to solve for what is my hydroxide ion concentration when that's my pH. So what we should know is that when a pH is above 7, we have a fairly high concentration of hydroxide. So that's what we plug in right here, and we don't double it. We don't do anything with that 2. The 1-to-2 ratio is how the magnesium hydroxide dissociates into solution. But this hydroxide ion came from another source before we put our magnesium hydroxide in there. We do have an X and a 2X in our change row. X is the amount of magnesium. Here it would be plus 2X, but this is another case where we have a very small KSP, meaning very little of our ions dissociate, and the amount, the 0.001 moles of hydroxide per liter, is fairly high comparatively. So that plus 2X is not very significant. That's how much, or approximately how much hydroxide we'd have in equilibrium. So just like on 7a, we can plug that number straight in for what we have here, avoiding any quadratic equations. So we have our value. We don't know what magnesium is. We do know what hydroxide is. We still square it because that's still our KSP expression. We square it. It's 1 to the negative 6th x. When we divide it over and solve for our x, that gives us our molar solubility. That tells me how many moles of magnesium ion dissolve into solution, how many moles per liter of the magnesium hydroxide has dissolved. If we wanted to add that to our hydroxide, that could tell us exactly how much hydroxide we have right now. But because that's such a small value, when we're looking in terms of sig figs, it wouldn't really change it. So our approximation was correct.